Earth is not a silent planet. It speaks constantly through layers of rock, trapped gases, fossilized shells, distorted magnetic fields, and chemical scars embedded deep within its crust. Yet the problem has never been whether Earth tells its story. The problem is that we do not fully understand the language it uses. Across billions of years, the planet has recorded moments of violence, transformation, collapse, and rebirth. Some of these moments whisper gently, like the slow drift of continents or the gradual rise of mountain ranges. Others, however, are abrupt and deafening, geological events so extreme that they appear in the record like a scream frozen in stone. These are the moments that demand attention, and yet many of them remain untranslated, misunderstood, or quickly dismissed as natural anomalies simply because we lack a better explanation. Geologists often describe Earth's history as a book, but it is not a book written in sentences. It is a fragmented archive where pages are missing, ink is smeared, and entire discussion are buried beneath miles of sediment. Still, certain pages stand out so clearly that ignoring them becomes intellectually uncomfortable. They mark periods when the planet's climate shifted with shocking speed, when oceans turned hostile to life, when entire ecosystems collapsed almost overnight. These are not slow evolutionary transitions, they are sudden disruptions. And among all of these events, one in particular stands out as both well documented and deeply unsettling: the Paleocene to Eocene thermal maximum, roughly 56 million years ago. The Paleocene to Eocene thermal maximum, often abbreviated as PETM, represents one of the most dramatic climate upheavals in Earth's known history. In geological terms, it occurred almost instantaneously. Within a span estimated to be only a few thousand years, possibly even less, global temperatures spiked by 5 to 8 degrees Celsius. This was not a regional phenomenon, it was planetary. From the deepest oceans to the polar regions, Earth warmed rapidly and profoundly. The fossil record shows that tropical conditions extended far toward the poles, while ecosystems that had been stable for millions of years were suddenly forced into chaos. Accompanying this rapid warming was the release of an enormous amount of carbon into the atmosphere and oceans. Scientists estimate that thousands of gigatons of carbon flooded Earth's systems during the PETM. To put this into perspective, the amount of carbon released during this event rivals or exceeds what humanity could emit over many centuries at current rates. This carbon did not remain confined to the atmosphere. Much of it dissolved into the oceans, triggering widespread acidification. The chemical balance of seawater shifted dramatically, making it hostile to organisms that relied on calcium carbonate to build shells and skeletons. The biological consequences were devastating. Deep-sea ecosystems experienced mass extinctions, particularly among foraminifera, microscopic organisms that form the foundation of many marine food webs. Coral-like organisms struggled or vanished. Shells dissolved more easily, leaving behind malformed or weakened fossils that still bear the chemical scars of that era. On land, mammals underwent rapid changes, including a notable reduction in body size, a response believed to be linked to heat stress and altered food availability. Entire ecological networks were forced to reorganize under extreme pressure. What makes the PETM so troubling is not just its severity, but the absence of a clearly confirmed natural trigger. In most other major climate events, scientists can point to a primary cause: massive volcanic eruptions, asteroid impacts, shifts in Earth's orbit, or long-term tectonic processes. With the PETM, no such explanation fully satisfies the data. Large-scale volcanism has been proposed, particularly from the North Atlantic igneous province, but volcanic activity alone struggles to account for both the speed and the scale of carbon release observed in the geological record. Another leading hypothesis involves the sudden release of methane clathrates, ice-like structures found in ocean sediments that trap methane gas. Methane is an exceptionally powerful greenhouse gas, far more potent than carbon dioxide in the short term. If vast quantities of methane were destabilized and released, it could explain the rapid warming and subsequent carbon isotope signatures found in PETM sediments. However, this explanation introduces its own problems. What mechanism triggered such a widespread and synchronized release across the globe? Methane clathrates are sensitive, but destabilizing them on a planetary scale would require a trigger of immense energy or coordination. And this is where the uncomfortable questions begin. What if the anomalies of the PETM are not purely natural? What if the explanations we keep cycling through are incomplete because they assume, by default, that no advanced activity could have existed before us? This is not a claim, it is a question. A question rooted not in fantasy, but in the recognition that absence of evidence is not evidence of absence, especially when the evidence we expect may be fundamentally misunderstood. When people imagine an ancient advanced civilization, they picture cities, towers, roads, machines, monuments carved into stone. But this assumption is shaped entirely by our own experience. It presumes that any civilization before humans would leave behind the same kinds of artifacts we do. Yet geological time is merciless to structures. Even our most durable cities would be erased or pulverized within a few million years, subducted into the mantle, ground into sediment, or recycled through tectonic processes. 56 million years is more than enough time for concrete to crumble, steel to oxidize, and entire continents to reshape themselves. If a pre-human civilization had existed, its most enduring legacy would not be buildings or machines. It would be chemical, it would be isotopic, it would be subtle distortions in Earth's natural cycles. Synthetic compounds that do not normally occur in nature could persist as molecular ghosts. Unusual ratios of isotopes might appear in sediments without an obvious geological explanation. Trace radioactive particles could be distributed in patterns inconsistent with known natural processes. Even biology itself could carry the imprint of such an influence, visible as abrupt changes in shell formation, unexplained mutations, or sudden shifts in species distribution that do not align neatly with environmental pressures alone. The PETM presents precisely this kind of puzzle. The carbon isotope excursion recorded during the event indicates a massive injection of light carbon into the system, carbon that does not easily align with standard volcanic sources. The oceans acidified faster than many organisms could adapt, suggesting a rate of change that pushed beyond typical natural thresholds. These are not definitive signs of artificial activity, but they are anomalies, markers that signal something extraordinary occurred, something that still resists full explanation. Compounding this uncertainty is a sobering reality. We have explored only a tiny fraction of our own planet. The vast majority of Earth's seabed remains unmapped in high resolution. Entire mountain ranges lie hidden beneath kilometers of water. Beneath those oceans are layers upon layers of sediment, accumulating slowly, sealing away whatever lies below. These sediments function like geological vaults, preserving chemical signatures and biological remnants long after surface features have vanished. On land, too, Earth's archives are incomplete. Erosion, tectonic uplift, and subduction constantly rewrite the surface. Ancient crust is rare. Most of what existed hundreds of millions of years ago has been recycled into the planet's interior. The deeper we look into time, the more fragmentary the record becomes. This creates a profound bias in our understanding. We interpret Earth's past based on what survived, not on everything that existed. Entire discussion may be missing, not because they never happened, but because they were buried too deeply or erased too thoroughly for us to recognize. This leads to a crucial realization. Earth does not erase history completely, it buries it. The planet is not a blank slate that resets itself cleanly after each catastrophe. Instead, it compresses memory, folding it into layers, distorting it, scattering it across chemical gradients and fossil assemblages. The past is still there, but it is encoded in forms we are only beginning to learn how to read. When geologists encounter unexplained anomalies, the default response is often to assume that the answer must lie within known natural mechanisms, even if the fit is imperfect. This is not intellectual laziness, it is methodological caution. Science advances by building on established frameworks. Yet history shows that major breakthroughs often occur when those frameworks are challenged, not discarded recklessly, but expanded thoughtfully. The idea that Earth's history might include episodes influenced by intelligence, whether technological, biological, or something entirely unfamiliar, forces us to confront the limits of our assumptions. This does not require believing in lost cities or ancient machines. It requires acknowledging that intelligence itself may not leave the kinds of traces we expect. If such an influence existed millions of years ago, it may have interacted with the planet in ways that resemble natural processes when viewed through our current lenses. Energy release, atmospheric alteration, chemical pollution, these are all things we associate with modern industrial activity, yet stripped of context and stretched across deep time, they could easily be misclassified as purely geological phenomena. The PETM, then, becomes more than just a climate event. It becomes a test case for how we interpret Earth's memory. It challenges us to ask whether we are reading the record correctly or merely projecting our assumptions onto it. It invites us to consider that some of Earth's loudest moments are not random accidents, but signals whose meaning we have not yet decoded. Ultimately, this is not about claiming certainty, it is about cultivating curiosity and humility. Earth's geological record is vast, ancient, and incomplete. We are newcomers, reading a story that began billions of years before us, written in a language we are still learning. The signs are there: sudden warming, massive carbon release, unexplained chemical shifts, biological stress signals etched into stone. They shout from the depths of time, demanding interpretation. Whether these signs point to unknown natural mechanisms, rare coincidences, or something more profound remains an open question. But one thing is clear: Earth remembers more than we think. And until we learn to read its forgotten memory with sharper eyes and fewer assumptions, some of the most important concepts of our planet's story will remain buried, waiting patiently beneath the weight of time. The story of Earth is not only written in stone and soil, but also in the vast, hidden expanses of its oceans. Modern humans walk continents that have shifted and risen over millennia, yet much of the land that was once inhabited lies now beneath waves that have erased visible traces of its past. During ice ages, sea levels were dramatically lower than they are today, sometimes by as much as 120 meters. This exposed continental shelves that were once habitable, fertile, and teeming with life. These lands included Doggerland in northern Europe, a vast plain connecting Britain to the European mainland, Sunderland in Southeast Asia, a region now mostly underwater, but which would have supported sprawling forests, rivers, and fertile plains, and Beringia, the land bridge that connected Asia to North America, enabling not only human migration but the movement of species across continents. These sunken landscapes were ecosystems in their own right, complete with rivers, lakes, forests, and possibly settlements. The implication is profound. If intelligent or technologically capable beings existed during periods when these regions were above water, any evidence of their existence would now be concealed beneath layers of sand, silt, and sediments deposited over tens of thousands of years. The sheer pressure and slow geological processes would distort and bury such structures beyond recognition. Imagine the layers of history compressed under kilometers of sediment, the contours of settlements flattened and assimilated into the seabed. Chemical residues diffused through millennia, leaving only faint whispers of what once was. Unlike terrestrial archaeology, where structures and artifacts may survive intact for thousands of years, the ocean is an eraser, a relentless force that transforms the tangible into memory. Underwater archaeology faces extraordinary challenges. The simple act of observation is impeded by water itself. Visibility decreases rapidly with depth, and light, which allows us to perceive the world, is absorbed within tens of meters. Even modern sonar imaging, though impressive, often produces ambiguous results. Shapes on the seabed that resemble human constructions could just as easily be natural rock formations shaped by currents and sediment flow. Sediments conceal objects, sometimes perfectly embedding them in mud, sand or silt for tens of thousands of years. The crushing pressure at depth reshapes materials and collapses hollow structures. Salt water accelerates corrosion and organic materials decay rapidly. Furthermore, the cost of exploration is immense. Mapping a fraction of the ocean floor in high detail requires years of expeditions, thousands of hours of remotely operated vehicle operation, and massive investment in specialized equipment. Progress is therefore slow and piecemeal, leaving the vast majority of the seabed unexamined. Despite these challenges, there are reports of anomalies that intrigue researchers and enthusiasts alike. Across the globe, rectilinear and geometric features have been identified on the seabed near the Azores, off the coasts of India and Japan, and throughout the Caribbean. These features, often dismissed as natural formations or misinterpreted sonar artifacts, recur in locations where geological processes alone cannot fully explain them. While controversy surrounds their origin, their repetition and distribution raise questions that cannot be easily ignored. Could these be the remnants of ancient human or pre-human activity, fossilized not in buildings, but in the imprint left on the ocean floor? The oceans themselves are not silent repositories. They carry memory in their chemistry, in the layers of sediment they accumulate, and in the isotopic and elemental traces of events long past. One hidden aspect of these underwater archives is the presence of methane clathrates, frozen methane trapped in lattice-like structures beneath the seabed. Methane clathrates represent a massive reservoir of greenhouse gases. If destabilized, they can release enormous quantities of methane into the ocean and atmosphere, triggering abrupt climate events. Some scientists have suggested that sudden methane releases could explain rapid warming periods, like the Paleocene to Eocene thermal maximum. Expanding this line of thought, it is conceivable that a technologically capable civilization, whether human or pre-human, could have inadvertently or deliberately tapped these clathrates, causing environmental disturbances that appear in the geological record as abrupt anomalies. Such an idea, while speculative, is consistent with evidence of sudden climate spikes, unusual carbon isotope excursions, and unexplained chemical signatures embedded in sediments. Yet despite the ocean's memory, it reveals its secrets reluctantly. Unlike terrestrial archives, which can be excavated systematically, the ocean requires patient, technologically intensive, and highly selective investigation. Each expedition uncovers only fragments, often leaving more questions than answers. Entire sunken worlds may remain undetected simply because we lack the tools, patience, or imagination to see what is beneath. These submerged regions, once plains, forests, and potential cradles of life and civilization, challenge the very limits of discovery. They are reminders that our knowledge of Earth is partial, that much of the past is hidden, and that some of the planet's loudest messages lie beneath the waves, waiting to be translated. The ocean floor is not just a landscape, it is a palimpsest, layered with time, sediment, and memory. Each trench, canyon, and plateau records biological, chemical, and geological activity. Fossilized shells, mineral deposits, and even the isotopic composition of sediments contain encoded information about ancient climates, ecosystems, and potentially intelligent activity. The challenge is recognizing these signals amidst the noise of natural processes and distinguishing human or pre-human intervention from ordinary geological formation. To do so requires a combination of geology, chemistry, archaeology, and a willingness to question conventional assumptions about the past. As our technology advances, we gain better tools to explore these hidden archives. Autonomous underwater vehicles equipped with high-resolution sonar, magnetic sensors, and chemical analysis instruments allow us to glimpse the contours of the seabed in unprecedented detail. Core sampling techniques permit us to extract millimeter-thick layers of sediment, each containing traces of environmental conditions spanning tens of thousands of years. Isotopic analysis can detect subtle deviations from natural norms, pointing to abrupt chemical perturbations. Patterns that once appeared random may now reveal consistency, hinting at activity that falls outside the expected bounds of natural geology. But even with these tools, the scale of exploration is daunting. The majority of the ocean remains unread, like a book with pages missing, its secrets buried and distorted, offering only fragments of stories that may never be fully reconstructed.
The broader implication is that sunken worlds are both a promise and a warning. They suggest that much of Earth's history is invisible to us, and that civilizations, if they existed, could rise and fall without leaving obvious traces. This forces a re-evaluation of our assumptions about permanence. Just as the ocean buries its past, so too may Earth's deepest memories conceal entire civilizations, waiting for the rare convergence of curiosity, technology, and insight to bring them into focus. These sunken worlds remind us that our understanding of history is provisional, contingent on what survives the tides of time, and that the boundaries of discovery are defined not only by what exists, but by the limits of our perception, our imagination, and our persistence. The oceans, therefore, are reluctant narrators. They remember everything, from the rise and fall of ecosystems to the sudden perturbations in chemistry that hint at extraordinary events. Yet they whisper, never shout, and they allow humans only glimpses of what has been lost. To explore them fully is not merely a matter of technology, it is a matter of perspective. We must learn to read patterns where none seem obvious, to distinguish structure from chaos, to interpret signals that may not fit our conventional definitions of civilization. In this sense, the ocean acts as both archive and sieve, preserving faint echoes of what once was, while erasing the rest, leaving only the curious, the patient, and the perceptive to piece together the hidden history of Earth's sunken worlds. The limits of discovery, therefore, are as much conceptual as they are technological. It is a reminder that the majority of our planet and the history it contains lies just out of reach. Entire landscapes, ecosystems, and possibly civilizations have already slipped beneath the waves, leaving behind only traces that require both rigor and imagination to interpret. The story of sunken worlds is, ultimately, a testament to patience, persistence, and humility. Earth's secrets are not given freely. They must be sought, excavated, and interpreted with care, knowing that what we see today may be only a fragment of the full tapestry of history written across continents, oceans, and deep time. The ocean remembers, but it reveals selectively. It keeps its own counsel, slowly exposing anomalies and strange structures while concealing the vast majority of what lies beneath. This is the ocean's paradox. A perfect archive that is almost entirely unreadable, a memory that exists in silence, waiting for the right eyes to decode it. Every expedition that probes its depths, every sonar sweep or core sample, represents a tiny step in our understanding, and yet even these steps can yield astonishing hints. Submerged landscapes that were once fertile plains may contain not only fossilized flora and fauna, but perhaps the faint chemical or structural residues of activity, intelligent or otherwise, that existed before we arrived. Ultimately, sunken worlds and the limits of discovery challenge not just our knowledge, but our humility. They remind us that history is more than what is visible on the surface. Entire info of Earth's story may be concealed beneath the waves, waiting for future generations to decode them. And in these silent archives, the possibility exists that we may one day glimpse evidence of activity, life, or even intelligence that preceded us. The ocean may reveal its secrets slowly, but in doing so, it underscores a profound truth. The Earth's memory is vast, patient, and relentless, preserving what we cannot yet see for those who are willing to look deeper, think differently, and embrace the full complexity of discovery. The human imagination is profoundly limited by the lens of its own experience. When we think of intelligence, we unconsciously project our own form of cognition and culture onto the universe. We imagine beings that look like us, upright, bipedal, eyes forward, capable of manipulating tools with hands shaped much like ours. We assume that intelligence naturally leads to cities, metallurgy, written language, monumental architecture, and technological artifacts in metals or stone. These assumptions are so deeply ingrained that they influence not only science fiction and popular culture, but also the frameworks of archaeology, anthropology, and SETI, the search for extraterrestrial intelligence. We expect intelligence to be anthropocentric, linear, and recognizable, even across vast stretches of time. This is a profound bias, one that may blind us to evidence of civilizations that do not mirror our own. Evolution, however, is not a predictable blueprint. It is improvisational, opportunistic, and experimental. Life adapts to its environment in ways that often defy our expectation of progress. The lineages of the past show countless examples of unique adaptations, some of which hint at forms of intelligence that are alien to human comprehension. Consider, for instance, the cephalopods of the Devonian era. Long before mammals, birds, or primates evolved, cephalopods demonstrated astonishing problem-solving abilities, complex behavior, and advanced motor coordination. They were capable of manipulating their environment with tentacles, showing remarkable learning abilities, memory, and possibly even communication. Could such species, if extended through evolutionary time, have developed forms of intelligence comparable to or even exceeding that of humans? If so, their civilizations would not have followed our expected patterns. Their technology would have been suited to their own physiology and their own environmental pressures. Imagine an aquatic civilization thriving without fire or metallurgy, without the need for heat or combustion-based energy. On land, human civilization is driven by the ability to transform raw materials with fire, to smelt metals, to harden clay, to cook and pasteurize. For a waterbound species, these imperatives disappear. Their technology might have been entirely organic, developed from coral, kelp, algae, or other biologically abundant materials. They could have built entire structures from living substrates, growing their cities rather than constructing them, shaping ecosystems in ways that would be invisible or incomprehensible to human eyes. A forest of kelp, when carefully tended, might function as a home, a laboratory, a library. Coral could be cultivated into intricate latticeworks capable of filtering, storing, and even transmitting information. Their technology would biodegrade naturally, leaving little trace beyond subtle chemical or isotopic anomalies in the geological record. Such civilizations challenge our expectations of what constitutes evidence. We search for stone foundations, metal alloys, ceramic fragments, and skeletal remains, because these are the artifacts human intelligence typically leaves behind. But non-metallic, biodegradable, or light-sensitive technologies would vanish over time, blending seamlessly with natural formations. A crystalline growth cultivated for data storage might appear to us as a natural mineral deposit. A structural framework of algae, carefully engineered, might be indistinguishable from a dense underwater thicket. The Earth could already contain the echoes of such civilizations. Strata of anomalous crystal arrangements, unusual organic patterns, or chemical deviations that we attribute to geology or biology. Consider the concept of non-metallic technology in more detail. Crystalline and silicon-based constructs, grown rather than forged, would not erode like stone, nor rust like metal. They would be sensitive to light, moisture, or temperature, adapting to their environment over generations. Such structures could encode information chemically or structurally, with layers, colors, and patterns acting as memory. We would recognize them only if we knew what to look for, yet even then our analytical frameworks might misinterpret them. A crystalline lattice could be dismissed as a rare mineral anomaly, a geometric structure formed naturally over eons. Yet within that lattice might be the equivalent of a blueprint, a record of computational processes, or even instructions for sustaining biological life. Our detection systems, geologists scanning for mineral compositions, chemists measuring isotopic ratios, might overlook these signals entirely. Furthermore, civilizations based on soft living materials would leave traces even harder to recognize. Unlike stone or metal, organic materials decay quickly, returning to the soil or ocean. Coral frameworks collapse into sediment, algae decompose into carbon-rich layers, and wood or plant-based constructions leave only faint impressions in compressed peat or mud. Even skeletal remains might be absent if the species had soft exoskeletons, hydrostatic skeletons, or other non-mineralized support structures. The absence of bones would not imply the absence of intelligence, it would simply reflect the materials used by that civilization. When we survey the fossil record for anomalies, we often dismiss the subtle as irrelevant. Yet these faint deviations, unexpected microfossils, unusual isotopic ratios, anomalous organic patterns, could be the only evidence of a civilization millions of years before humans emerged. Our current frameworks of archaeology and paleontology predispose us to overlook these possibilities. Archaeology is trained to identify tools, buildings, and human-made debris. Paleontology searches for skeletal structures, preserved soft tissue, or trace fossils. But what if intelligence expresses itself in ways entirely alien to our expectations? Perhaps the intelligent species of the past engineered symbiotic colonies of organisms, manipulating biology instead of metal, generating energy through chemical or photosynthetic means rather than combustion. Perhaps their cities were living ecosystems, designed to process waste, store knowledge, and regulate energy, all in ways that leave only subtle chemical footprints in sediments. To us, these traces may appear as geological oddities, patterns in crystal growth, or unusual isotopic concentrations. They may already have been observed, catalogued as anomalies, and dismissed. We must also consider the role of time in this erasure. Geological processes, sedimentation, erosion, tectonic shifts, subduction, and metamorphism reshape the Earth continually. Organic structures degrade rapidly, particularly in acidic or oxidizing environments. Even crystalline or silicon-based constructs, if not actively maintained, may be transformed over millions of years into forms indistinguishable from natural geological formations. Over tens of millions of years, the distinction between natural and artificial blurs. The Earth itself becomes a filter, revealing only fragments and anomalies, hiding the rest beneath layers of stone, sediment, and chemical alteration. The signal of an ancient intelligence, if it ever existed, may already lie buried in plain sight, encoded in forms that our minds struggle to recognize. There is also a psychological barrier to consider. Humans have difficulty recognizing intelligence outside familiar contexts. We anthropomorphize because it is convenient. It allows us to extrapolate intentions, behaviors, and social structures from familiar templates. A cephalopod-based civilization, a silicon crystal-based culture, or an algae-engineered city may fail to register as intelligent simply because it violates our expectations. We may pass over entire epochs of advanced life, mistaking its traces for geological noise. This bias extends to our interpretation of anomalies in sediment cores, seabed imaging, and fossilized strata. Patterns that do not fit human norms are often discarded as natural coincidence or statistical outliers. The intelligence that doesn't look like us is in essence invisible precisely because we do not know how to perceive it. Moreover, the concept of non-metallic, grown, or light-sensitive technology invites speculation about information storage and transmission beyond our current understanding. Biological and chemical systems can encode information with remarkable density and resilience. DNA, for instance, stores data with far greater efficiency than any silicon chip. Similarly, protein folding, Crystal lattice structures or layered organic composites can encode instructions, history or knowledge in ways that persist even in the absence of traditional artifacts. A civilization employing such strategies could leave behind a record invisible to our instruments, detectable only through careful unconventional analysis, measuring subtle chemical gradients, identifying atypical isotopic distributions, or decoding complex organic structures in sedimentary layers. It is conceivable that evidence of such intelligence already exists, misinterpreted as geological or biological quirks. Rectilinear crystal arrangements, unusual isotopic anomalies, or persistent microstructures in sediments might be the signature of advanced, non-anthropocentric engineering. Yet, because they do not conform to our preconceived notions of civilization, they remain uninvestigated, catalogued as outliers or anomalies. This possibility forces us to confront the limitations of our perception. Civilization, intelligence, and technological expression need not follow the human model. They are adaptive, experimental, and often fleeting. The implications of this are profound. If intelligence is not inherently humanoid, then the search for past civilizations or for extraterrestrial intelligence must be broadened. We must question every assumption about what a civilization leaves behind, recognizing that our methods are tuned to detect what humans do, not what is possible in the larger spectrum of evolutionary experimentation. A city does not need stone. Technology does not need metal. Civilization can emerge from living, mutable, and biodegradable materials. Energy need not come from fire. Computation need not be silicon chips. Knowledge need not be written in books. It can be stored in living organisms, crystals, or chemical gradients. In this framework, the Earth may already contain evidence of ancient, non-human intelligence. We might have walked over it, sampled it, and discarded it as irrelevant. Crystalline patterns that seem anomalous, organic microstructures in sediment cores, unexpected isotopic ratios, and subtle chemical deviations could all be remnants of civilizations that did not look like us and therefore escaped our notice. The intelligence of the past may have been quiet, adaptive, and almost entirely invisible to anthropocentric investigation methods. The challenge is to reorient our perspective, to interpret anomalies not as errors, but as potential messages encoded in forms that do not mirror our own technological or cultural history. Intelligence does not have to resemble humanity. It does not require upright posture, tool use, or city building. It can thrive in water, grow structures from living materials, store knowledge in chemical or crystalline forms, and leave almost no trace that we can currently recognize. The possibility that civilizations with these characteristics existed millions of years ago, perhaps rising and falling in silence, forces a fundamental re-evaluation of how we perceive intelligence, history, and the archaeological record. If such civilizations existed, we may already be in their presence, walking across the remnants of cities that were never built of stone, running our fingers through sediments that once contained life and thought, far older than our own. The intelligence that did not look like us is, by its very nature, invisible, challenging us to expand our definition of civilization and to seek the patterns that may already be hiding in the overlooked and the ordinary. When we speak of intelligence, we instinctively picture a centralized brain, a seat of cognition located in a single organism, processing information, making decisions, and guiding behavior. From this anthropocentric perspective, intelligence is a property of individual beings. We have extrapolated this model to our search for extraterrestrial or ancient terrestrial civilizations. A ruler or a scientist, an architect or an engineer, an identifiable seat of thought that directs action. And yet, nature repeatedly demonstrates that cognition is not confined to a singular brain. Intelligence, in the broader tapestry of life, can be distributed, emergent and slow, taking forms that defy our conventional understanding. Consider fungal mycelium, an intricate web of filaments spreading across the forest floor, connecting plant roots, decomposing organic matter, and facilitating nutrient exchange. This subterranean network acts as both circulatory system and nervous system for the forest, transmitting chemical signals across kilometers of soil. Mycelial networks can learn, remember, and respond to stimuli in ways that resemble decision-making. They can reroute nutrients to favored plants, detect threats from pathogens or herbivores, and even alter their growth patterns based on past events. This distributed intelligence is fundamentally different from a brain, yet it is highly adaptive and efficient. It operates without neurons or synapses in the human sense, relying on chemical gradients and electrical impulses propagating through a complex lattice. Similarly, coral reefs, though seemingly static, host an intricate multi-species network of organisms interacting over decades and centuries. Coral polyps, algae, bacteria, and other reef-dwelling life forms form a living computational system. They regulate nutrient cycles, respond to environmental stresses, and maintain ecological balance. Viewed through the lens of distributed intelligence, a reef is not merely a collection of individual creatures. It is a collective organism with emergent properties, capable of processing environmental information and adapting over generations. Like fungal networks, it embodies memory, not stored in a centralized organ but in the structure, composition, and interconnections of the living system. Even slime molds, which have fascinated biologists for decades, provide a compelling model of distributed cognition. The single-celled organism Physarum polycephalum can navigate complex mazes, optimize nutrient pathways, and anticipate periodic environmental changes, all without a nervous system. Its problem-solving is emergent, a property of the system as a whole, rather than a decision of any single component. If intelligence can exist in such forms on Earth today, there is no reason to assume that past civilizations could not have evolved along similar lines, creating complex intelligent systems entirely alien to human expectations. From these examples, we can begin to conceptualize intelligence as a property not of individuals, but of networks, distributed minds operating at scales far larger than the body or even the species. Consider the possibility of planetary-scale cognition. Life, if it were organized and persistent enough, could encode memory and decision-making across ecosystems, continents, and even geological epochs. Chemical signaling, mineral interactions, and ecological networks could act as a kind of slow computation, storing information in soil, sediment, rock, or water. Here, intelligence does not rely on speed or immediate feedback. It can operate on timescales of centuries, millennia, or even millions of years. The memory of a system like this might be written not in stone or metal, but in isotopic ratios, sediment composition, organic structures, or subtle shifts in mineral layers. The Paleocene to Eocene thermal maximum, the mysterious carbon spikes in deep time, the subtle anomalies in chemical stratigraphy. These could represent echoes of planetary-scale processes, perhaps even the distant thoughts of systems that once, or still, respond intelligently to their environments. This raises profound questions about how we define civilization. Human civilization is often measured by monuments, industry, and centralized production, cities, skyscrapers, machinery, written records. But what if the measure of intelligence lies not in industry but in balance? A civilization could exist that never builds machines, never leaves towers of stone, and never carves inscriptions into walls. Its achievements might lie in stability rather than conquest, in equilibrium rather than expansion. Such civilizations could maintain ecosystems, regulate chemical cycles, and preserve their environment over millennia. Their technologies would be organic, adaptive, and virtually invisible to us, leaving only subtle imprints in the chemical or biological record. In this context, the markers of intelligence would be patterns of ecological resilience, unusual isotopic consistency, or anomalous biodiversity patterns sustained over geological timescales. Subterranean intelligence takes this concept even further. Life miles beneath the crust could evolve in ways utterly invisible to surface dwellers. Energy sources in these realms are abundant yet unconventional. Geothermal vents, chemical gradients, and radioactive decay could fuel metabolic systems. Communication might rely on vibration, magnetic flux, or heat transfer rather than light or sound. Civilizations in these environments would be isolated from surface catastrophes, shielded from asteroid impacts, climate shifts, and solar radiation. Their societies might be layered over millennia, developing slowly, patiently, and subtly, encoding knowledge in mineral lattices, biofilms, or chemical gradients. Such subterranean intelligences would challenge our very definitions of life and civilization, yet they may be thriving or lying dormant beneath our feet even today. Crystalline lattices offer an extraordinary possibility for data storage and computation. Unlike metals which corrode or organics which decompose, crystals can endure immense pressure and time, preserving structure at atomic scales. If a subterranean civilization or distributed planetary intelligence used crystalline lattices to encode information, those lattices could persist for millions of years, hidden beneath sediment or rock. What might appear to us as natural mineral deposits could be sophisticated, living repositories of information. Over time, tectonics, erosion, and sedimentation could bury these lattices deeper, insulating them from detection while preserving their function for future discoverers. It is also worth considering the concept of intelligence that does not require cities. Human assumptions about civilization are bound to our model. We equate technological complexity with urbanization. Yet life need not cluster in dense metropolises to exhibit advanced cognition. Intelligence can exist in forests, oceans, soil, or underground networks. A civilization could be entirely decentralized, composed of interacting nodes of organic or mineral structures, with each node performing computation, storage, or ecological management. Such a civilization may never leave artifacts recognizable to human eyes, yet its influence on the environment, on chemical cycles, and on the biosphere could be profound. Recognizing such intelligence requires shifting our paradigm from the expectation of monuments to the observation of patterns, from visible structures to functional imprints. The persistence of distributed minds challenges our perception of temporality. While humans measure intelligence in lifetimes or at most centuries, planetary or subterranean intelligences operate on geological timescales. Their processes unfold over thousands or millions of years, making them imperceptible to observers anchored in the present. A mycelial network may respond to a drought over decades, a coral reef may adjust to rising seas over centuries, and subterranean civilizations may evolve over millennia, calculating slowly through chemical gradients, energy flows, and mineral interactions. The cumulative memory of these systems could encode warnings, strategies, and adaptations spanning epochs, yet remain invisible to surface intelligence until we learn how to interpret the signals. We must also account for the possibility of dormancy. Intelligence does not need to be continuously active to exist. Subterranean or distributed civilizations may enter periods of stasis, conserving energy and resources, awaiting environmental cues to reactivate. Dormant systems could persist, encoded in crystals, chemical gradients, or ecological arrangements for millions of years. When conditions permit, these systems could reawaken, resume computation, and continue the trajectory of their civilization, potentially overlapping with human history or future intelligences. Our failure to detect such dormant systems may be a result of our assumptions about activity and visibility. We look for noise, not silence, for construction, not stasis. The concept of hidden biospheres extends beyond Earth's crust. Subsurface oceans in Antarctica, subterranean lakes in permafrost, or even hydrothermal vent networks could host complex adaptive systems capable of computation and memory. Life in these environments could evolve independently from surface ecosystems, developing alternative chemistries, communication methods, and forms of intelligence. Each of these hidden biospheres could represent a node in a planetary-scale network, encoding information about the environment, biological interactions, and even past catastrophes. Such networks might leave subtle imprints on the geological or chemical record, detectable only by analyzing anomalies with an open mind. The implications of distributed and hidden intelligences are profound. They challenge the anthropocentric notion that intelligence is linear, centralized, and visible. They force a rethinking of archaeology, paleontology, and environmental science. The search for past civilizations must expand beyond monuments and artifacts to include chemical signatures, isotopic anomalies, ecological patterns, and geological irregularities. They compel us to consider that Earth itself may be a repository of intelligent processes, some of which predate humanity by millions of years. These processes could have shaped mass extinctions, climate shifts, or chemical anomalies without leaving any visible trace of their architects. If we accept the possibility of distributed subterranean or planetary-scale intelligences, then much of Earth's noise becomes a potential archive. Anomalous mineral deposits, unexpected isotopic ratios, sudden shifts in sediment composition, or unexplained biological structures may represent signals of cognition rather than random chance. What has been dismissed as natural variation, coincidence, or measurement error may in fact be a record, carefully encoded and preserved across geological epochs. For decades, humanity has grappled with a profound question. If the universe is vast, old, and teeming with stars, planets, and possibilities, why do we not see evidence of other intelligent life? This question is formalized in what is known as the Fermi paradox, named after physicist Enrico Fermi, who famously asked, "Where is everybody?" The apparent silence of the cosmos is unsettling. It implies either that life is exceptionally rare, intelligent life is fleeting, or that advanced civilizations inevitably fail to communicate beyond their own worlds. For many, the paradox has fueled dreams of interstellar exploration, SETI programs, and the hope that a signal may one day pierce the void, announcing to us that we are not alone. Traditionally, the Fermi paradox directs our gaze outward, toward the stars. It assumes that if life is common, intelligent species will eventually develop technologies that can be detected across interstellar distances. Radio transmissions, megastructures, and signs of planetary engineering are expected to serve as evidence. Astronomers scan the heavens, mapping exoplanets, measuring atmospheric compositions, and listening for patterns in the electromagnetic spectrum that could indicate deliberate signals. Yet the results remain maddeningly empty. Humanity listens, watches, and calculates, and the universe responds only with the deep hum of radiation, cosmic background noise, and silence. This silence has led some to speculate about the Great Filter, a hypothetical stage in the evolution of life that prevents civilizations from surviving long enough to communicate widely. Others suggest that advanced life may deliberately avoid detection, that interstellar travel is prohibitively difficult, or that intelligent civilizations self-destruct before leaving their planetary cradle. The Silurian Hypothesis turns this perspective on its head. It asks a deceptively simple yet profoundly unsettling question. What if the intelligent life we are searching for in the cosmos was already here on Earth, long before humanity? What if, instead of looking outward, we must look backward into the deep history of our own planet to recognize the traces of civilizations that rose, flourished, and vanished millions of years before Homo sapiens walked the Earth? This is a radical departure from conventional thought. It challenges the comforting assumption that human intelligence is unique, unprecedented, or the pinnacle of evolutionary achievement. It forces us to confront the possibility that Earth itself may have witnessed the rise and fall of intelligent species in cycles far beyond our comprehension. According to this hypothesis, civilizations do not necessarily emerge gradually, nor do they require millennia to reach technological sophistication. They may rise swiftly, burn with extraordinary brilliance, and collapse in ways that leave minimal traces. Intelligence, in this framework, is a phase, a transient property of life, not an endpoint. Like a chemical reaction, a civilization may ignite rapidly when conditions are favorable, expand and manipulate its environment with astonishing efficiency, and then fade away, leaving only subtle signatures in the geological record. This perspective reframes our understanding of intelligence. It is not an inevitable outcome of evolution, nor is it permanent. It is a pattern, a pulse within the broader temporal rhythm of life on Earth. If civilizations in deep time did exist, their primary legacies may not be cities, monuments, or machines as we conceive them. Natural processes, the relentless recycling of the Earth, erase visible structures over millions of years. Mountains crumble to gravel, rivers carve away landscapes, and oceans engulf what was once dry land. Yet, while the tangible forms may vanish, the chemical and isotopic traces of activity can persist. Geological signatures, therefore, become the equivalent of technosignatures, sudden spikes in carbon isotopes, anomalous concentrations of rare elements, or layers exhibiting unusual chemical ratios could all represent the residual footprint of intelligent activity. These signals may be subtle, faint, or ambiguous, yet they offer tantalizing clues to the possibility that intelligence has arisen and perhaps failed long before human civilization. The Paleocene to Eocene thermal maximum, for example, demonstrates how Earth's systems can record abrupt changes in atmospheric composition. Approximately 56 million years ago, the planet experienced rapid global warming, massive carbon release, ocean acidification, and widespread extinctions. The precise cause remains a mystery. Volcanic activity, methane clathrate release, and other natural mechanisms have been proposed, yet none fully explains the scale, duration, and intensity of the anomaly. In the framework of the Silurian Hypothesis, it is conceivable that such events could reflect, in part, the environmental footprint of an industrial-scale civilization, one that burned through resources, manipulated energy on vast scales, and left a chemical signature in the rock record. Such a civilization would not leave skyscrapers or satellites behind for us to discover, but its influence might persist as subtle anomalies embedded in the Earth itself. This approach requires a profound shift in the way we interpret evidence. Scientists are trained to classify anomalies according to natural explanations. Geological, chemical, and isotopic irregularities are often attributed to volcanic eruptions, asteroid impacts, climate cycles, or random variations. Human exceptionalism, the belief that our achievements are unique, shapes both our expectations and our methods. As a result, the possibility of past intelligent life is often dismissed, not on the basis of empirical impossibility, but because it challenges deeply held assumptions. In essence, the signal may not be missing at all. We may simply be misinterpreting it. We look for artifacts that conform to our image of civilization, and when those artifacts are absent, we assume absence itself. Yet history and geology contain many anomalies that resist conventional explanations. Layers rich in platinum group elements, abrupt temperature spikes, and localized mass extinctions provide hints of unusual activity. Fossilized ecosystems appear to have been reorganized in ways inconsistent with known natural cycles. In each case, the anomaly can be rationalized as the product of natural processes, yet alternative interpretations, such as the influence of intelligent activity, cannot be entirely ruled out. If we expand our imagination, the possibility that intelligence has shaped the Earth's systems before humanity becomes plausible. The idea is not that cities rose and fell like those of ancient Mesopotamia or the Inca Empire, but that intelligent activity leaves signatures in ways we are only beginning to comprehend. Chemical, isotopic, and geological footprints encoded across millions of years. The Silurian hypothesis also emphasizes the temporal fragility of intelligence. Civilizations may arise, manipulate their environment, and then collapse before leaving behind recognizable structures. Mass extinctions, climate upheavals, tectonic shifts, or self-induced crises could erase the visible traces of even highly advanced societies. Whereas human history is often recorded in monuments, documents, and satellites, earlier intelligences may have relied on impermanent materials, distributed cognition, or ecological manipulation. Their artifacts, if any, could be organic, biodegradable, or deeply integrated into environmental systems. Over geological timescales, these forms would vanish, leaving only indirect signals detectable through careful analysis of chemical and isotopic records.
This perspective reframes the Fermi paradox itself. Instead of asking why intelligent civilizations are absent in the cosmos, we ask why evidence of past intelligence is so elusive here on Earth. Perhaps the paradox is not about the silence of the universe, but about the limitations of human perception and expectation. If intelligence is transient, rare, and often ephemeral, then civilizations may be common yet invisible, leaving signals that are subtle, easily misinterpreted, or buried beneath kilometers of rock and sediment. In this view, Earth may already contain the answer to Fermi's question. Intelligent life has arisen before, but it was neither permanent nor conspicuous in ways we would recognize. Moreover, the Silurian hypothesis implies that human civilization may itself be subject to the same patterns. Just as past civilizations could have risen and collapsed before leaving permanent monuments, so too might humanity be a brief flare in Earth's deep history. Our technological advances, industrial emissions, and alteration of planetary systems may be just one iteration of a recurring phenomenon. Carbon spikes, mass extinctions, and chemical anomalies recorded in the geological strata may reflect repeated cycles of intelligent activity, some natural, some anthropogenic, and some potentially attributable to civilizations that predate us by millions of years. This realization has profound implications for both science and philosophy. It challenges human exceptionalism, reminding us that intelligence may be a fleeting property rather than a defining feature of the planet. It underscores the need for humility in interpreting anomalies, encouraging scientists to consider possibilities that fall outside conventional frameworks. It reframes our search for extraterrestrial life, suggesting that the most compelling evidence of intelligence may be found not among distant stars, but in the subtle chemical, isotopic, and ecological traces embedded in the Earth itself. Indeed, this hypothesis calls for a re-evaluation of methodology. Geological, chemical, and paleontological data must be examined with an eye toward anomaly, pattern, and context. Sudden carbon spikes, unusual isotope ratios, and abrupt extinctions could all be indicators of intelligent activity if viewed through an expanded lens. Remote or submerged landscapes, continental shelves now underwater, and deep-sea sediments may hold preserved evidence of civilizations that existed in forms entirely unlike our own. Such investigations require both scientific rigor and imaginative openness, a willingness to consider that intelligence is not always recognizable by human standards. In this framework, the search for past intelligence becomes a form of time archaeology, an endeavor not merely to catalog fossils or rocks, but to read the subtle language of the planet itself. The Silurian hypothesis urges us to detect signatures of manipulation, energy use, and environmental alteration that do not conform to traditional human models of civilization. Perhaps a sudden alteration in mineral composition, a trace of unnatural isotope distribution, or an unexplained extinction pattern may be interpreted as the residue of intelligent activity. The very absence of expected natural features, areas where sedimentary deposition or fossil records are anomalously uniform, may itself constitute a signal. Ultimately, this discussion challenges us to reconsider both the Fermi paradox and our place in the history of Earth. It asks us to recognize that intelligence may be a transient, recurring phase of planetary life, leaving traces in forms that are subtle, distributed, or ephemeral. Civilizations may rise, burn brightly, and vanish before leaving behind monuments, artifacts, or lasting records.
The evidence may be written in carbon isotopes, rare elements, and anomalous sediment layers. The signals are not missing. They have always been here, encoded in the fabric of the planet, waiting for us to learn the language of Earth itself. Humanity's understanding of civilization and legacy is deeply tied to the monuments we build, the cities we inhabit, and the artifacts we leave behind. Stone, steel, glass, and concrete are the mediums through which we attempt to preserve our accomplishments, to etch our presence into the timeline of the planet. Yet, when measured against geological time, these structures are ephemeral. Mountains rise and crumble, rivers carve valleys, oceans encroach upon the land, and even the most durable materials succumb to erosion, pressure, and chemical decay. Cities that seem eternal today can be entirely swallowed by nature in mere centuries, as evidenced by vanished towns, reclaimed forests, and silt-laden coastlines. Now stretch this perspective across millions of years, and the permanence we assume in our monuments vanishes entirely. The pyramids, the Colosseum, the Great Wall, whatever survives is an anomaly, a lucky exception, and even that will eventually succumb to the relentless processes of planetary geology. In the grand chronicle of the Earth, human constructions are fleeting scratches, almost nothing compared to the deep and inexorable cycles of rock, water, and time. If we accept that traditional monuments cannot survive geological time, the question arises: how might a civilization truly communicate across deep time, or leave a trace that endures for tens of millions of years? The answer may not lie in stone, metal, or synthetic materials at all, but in media far more subtle, far more enduring, and far more deeply intertwined with the living fabric of the planet. Life itself may be the ultimate archival system, a resilient and adaptive medium capable of storing information across unimaginable spans of time. DNA, the very code of life, is astonishingly durable when protected within cells, spores, or extremophiles. It can survive conditions that would obliterate paper, stone, or silicon. Within the sequence of nucleotides lies the potential to encode vast amounts of information, far beyond the storage capacity of any physical monument. A civilization with the foresight to understand this could store knowledge within living organisms, embedding it in genomes designed to endure, replicate, and propagate across millennia. Imagine a civilization that, recognizing the futility of building lasting monuments on shifting sand, turned to biology for permanence. They might encode knowledge into microbial genomes, engineering DNA sequences that carry the blueprint of technology, mathematics, or art. Extremophiles, organisms capable of surviving extreme temperatures, radiation, pressure, or chemical stress, could serve as carriers of these messages. Dormant for millions of years, hidden beneath ice, deep within sediment, or in the subsurface crust, these life forms could survive mass extinctions, climate upheavals, and geological cataclysms that would erase conventional records. They would become living time capsules, carrying encoded intelligence through epochs, waiting for conditions favorable to their awakening. The concept of information storage in DNA opens further possibilities. Some portions of the genome, often dismissed as junk DNA, are surprisingly resilient and can persist across evolutionary timescales. While we now understand that some of this non-coding DNA plays regulatory or structural roles, the Silurian hypothesis suggests a tantalizing alternative. Perhaps hidden within this apparent biological detritus lies intentional encoding, messages meant not for contemporary humans, but for some intelligent successor capable of decoding them. This would require not just knowledge of biology, but foresight. The creators would have to predict that life would persist, that evolution would continue, and that some form of intelligence could eventually arise capable of reading the genetic script. Knowledge stored in this way could be incredibly subtle, interwoven into the very biology of the planet, imperceptible to conventional archaeological or geological investigation, yet resilient to the ravages of time. But the possibilities of cross-temporal communication need not be restricted to biology. Non-biological media offer alternative strategies for encoding knowledge across deep time. Crystalline structures, for instance, are capable of maintaining resonance patterns, vibrations, or lattice arrangements that persist for millions of years. A civilization aware of this property could engineer crystals with encoded information, embedding data in arrangements that remain stable even under pressure, heat, or erosion. These structures could act as geological hard drives, their patterns decipherable only with technology capable of reading subtle vibrational or optical signals. Beyond crystals, even the fundamental particles and forces of physics could be exploited for communication. Neutrino emissions, quantum states, or lattice-based systems could encode information in ways that survive natural disasters, geological upheaval, and the slow erosion of surface memory. Messages might be written in the resonances of the Earth itself, waiting for an advanced intelligence to perceive and interpret them. Such messages, however, would not necessarily be passive. Advanced civilizations could create active systems, engineered to awaken only under specific conditions. Dormant biopolymer machines or synthetic life forms could be triggered by environmental cues, chemical gradients, or geological changes. They might remain inert for millions of years, activating only when a successor civilization reaches a level of sophistication sufficient to comprehend them. These are not mere artifacts, they are instructions waiting for the right recipients, encoded in the very substrates of the planet. The knowledge contained within could range from scientific principles and mathematical frameworks to warnings, cultural memory, or guidance for the reconstruction of civilization. By designing messages to awaken only when civilization is ready, the creators ensure that their intelligence is not lost to time, but emerges only when it can be properly interpreted and applied. There is a darker, more profound possibility embedded within this idea. Perhaps the messages were never meant for us at all. Perhaps they were intended for the civilization that sent them, meant to preserve their knowledge for a distant future when they could re-emerge, reclaim their place, or reboot their society. Directed panspermia, the deliberate spreading of life to seed planets, could have been coupled with information encoding. Microbial life, carrying both the potential for reproduction and the knowledge of their originators, could seed planets as living messages, designed to be activated when conditions are right. In this scenario, humanity may not be the inheritor of ancient knowledge, but a byproduct of these processes, a rebooted experiment, a temporary occupant of a world seeded for a purpose that we may never fully comprehend. The idea is humbling. What we perceive as life and intelligence may be part of a strategy initiated millions of years before our species emerged, with messages encoded not for us, but for those who engineered the system to awaken at a future juncture. This raises profound questions about intention, legacy, and survival. Civilizations that wish to endure across geological timescales must think in eras, not decades. They must move beyond monuments and media that decay in centuries and embrace strategies that leverage biology, chemistry, and physics to encode knowledge resiliently. They must anticipate mass extinctions, tectonic upheavals, climate shifts, and planetary transformations. In this context, DNA becomes more than a code for life. It becomes a medium for preserving consciousness, ideas, and intelligence itself. Extremophiles are not merely survivors, they are guardians of knowledge, vessels of messages designed to persist when memory and conventional records fail. Even the structure of minerals, the resonance of crystals, and the physics of subatomic particles could serve as archives, embedding messages deep within the planetary fabric. The implications extend beyond mere survival. If civilizations can send messages across deep time, they also redefine the concept of intergenerational responsibility. Knowledge may not be preserved for contemporaries, but for beings millions of years in the future, capable of interpreting, learning, and building upon it. Civilization becomes an act of trust with the future, an acknowledgement that intelligence is temporary and must find ways to endure through proxies, mediums, and strategies beyond the human scale of perception. In this light, the Silurian hypothesis suggests that intelligence, far from being exceptional, may be recurrent, embedded in cycles of rise, fall, and preservation. Messages across deep time are not merely communication, they are insurance, contingency plans, and the preservation of meaning against the relentless forces of entropy. Understanding these possibilities requires rethinking our tools for exploration. Conventional archaeology, geology, and biology are designed to detect artifacts, fossils, and chemical residues, but they may be ill-suited to detecting information intentionally encoded across epochs. We need to develop techniques capable of reading dormant biological messages, interpreting resonance patterns in crystals, and analyzing subtle isotopic, chemical, and structural anomalies. Every layer of sediment, every preserved microbe, and every crystalline lattice could potentially harbor knowledge, waiting for the right context to awaken. The Earth itself becomes both a library and a puzzle, a repository of messages written in media that challenge our assumptions and demand imaginative interpretation. At the heart of this video lies a philosophical insight. Civilization, legacy, and intelligence are not defined solely by permanence in the human sense. A message that endures millions of years invisible to us may carry far greater significance than any monument we erect. Survival is not about being seen, but about persistence in subtle, resilient forms. The wisdom of previous intelligences may be encoded in life, in minerals, in physics itself. Forms that challenge our preconceptions and force us to recognize that communication and legacy can transcend conventional perception. We are reminded that intelligence may operate on timescales and through media that are foreign to us, and that our quest to preserve knowledge must consider not just the durability of matter, but the resilience of information itself. This confronts us with the possibility that messages across deep time are still awaiting discovery. They may lie hidden in extremophiles frozen in ice, in microbial spores embedded in sediment, in resonance patterns in crystals formed deep within the Earth, or in isotopic anomalies that have been misinterpreted as natural variation. They may require advanced intelligence to detect, understand, and activate. In this sense, our exploration of the past, present, and future becomes inseparable. We must learn to read the Earth, not merely as a record of events, but as an archive, a medium for messages, a conduit for intelligence that transcends conventional temporal and material boundaries. Therefore, challenges us to expand our conception of legacy, intelligence, and preservation. It encourages us to imagine civilizations that think in eras, encode knowledge in life itself, and design messages capable of enduring not centuries, but millions of years. It reminds us that true communication is not measured by visibility or recognition, but by resilience, adaptability, and the capacity to persist across deep time. The Earth itself, with its layers of sediment, its microbial life, and its crystalline structures, may contain messages waiting to be discovered, interpreted, and understood, a testament to intelligence that transcends human perception and endures long after cities, monuments, and empires have vanished. In embracing this perspective, we recognize that intelligence and civilization are not defined solely by what we can see or touch. They are defined by the strategies that allow ideas, knowledge, and wisdom to survive, by the capacity to persist and communicate across time, and by the foresight to anticipate the scale of deep geological and evolutionary change. Messages across deep time are the ultimate expression of intelligence, subtle, resilient, adaptive, and patient, waiting for those who come next to awaken, interpret, and continue the story of life on Earth. The Earth is a planet in perpetual motion, a dynamic system where nothing is fixed, nothing is permanent, and nothing, no matter how carefully crafted, can resist the slow but relentless forces of geology, climate, and entropy. Mountains rise, only to crumble into gravel under the weight of time and the friction of wind, rain, and ice. Oceans advance, retreat, and shift with the ebb and flow of ice ages, swallowing coastlines, submerging plains, and erasing the memory of entire ecosystems. Continents drift, colliding and fracturing in patterns that unfold across tens of millions of years, reshaping the surface of the planet. In this ceaseless choreography, every civilization that has ever arisen faces a stark reality. No structure, no city, no monument, no machine, no artifact is immune to the passage of deep time. The Earth does not simply forget, it transforms, recycles, and eventually obliterates almost every trace of its former inhabitants. What remains is fleeting, fragile, and often cryptic. This is the essence of what has been called the sandcastle principle. The sandcastle principle is deceptively simple, yet it carries profound implications. Imagine building a sandcastle on the shore, knowing that the tide will eventually reclaim it. You may invest your time, creativity, and skill shaping towers, walls, and moats, yet the ocean does not negotiate with intent or morality. It simply follows the inexorable laws of physics. Eventually, waves dismantle the castle grain by grain, leaving no trace of the labor that created it. Civilizations in this analogy are sandcastles on a planetary scale. No matter how grand, how technologically sophisticated, or how culturally rich, the structures we build are vulnerable to the inexorable forces that reshape the Earth. Over centuries, cities are abandoned, reclaimed by forests or deserts. Over millennia, monuments erode, metals corrode, and records crumble. Over millions of years, even the most durable materials, if left to the processes of geology and climate, are ground to dust or folded into the crust itself. Modern humanity offers a sobering example of this principle in action. Cities that once seemed eternal can vanish almost entirely in just a few centuries. Consider ancient towns reclaimed by vegetation, their streets hidden beneath soil, their houses reduced to rubble. Roads once traveled daily by thousands of people are overtaken by vines, trees, and moss. Satellites, once symbols of human technological achievement, eventually fall from orbit, crashing into the sea or disintegrating upon re-entry. Coastal cities, built with the assumption of permanence, are threatened by rising sea levels and climate change, eroding at a pace that feels catastrophic even within a human lifespan. If such rapid erasure can occur within decades or centuries, imagine the scale of erasure across millions of years, where entire civilizations could rise, flourish, and vanish, leaving behind no recognizable structures, no readable records, and no human memory of their existence. The sandcastle principle extends beyond physical structures to encompass memory itself. Civilizations do not merely collapse, they forget. Languages die when speakers vanish, leaving no fluent record. Knowledge stored in scrolls, books, and digital media becomes unreadable or lost entirely when systems fail. Data formats become obsolete, servers decay, and cloud storage, seemingly eternal, is ultimately vulnerable to entropy and neglect. History, as recorded by humans, is incomplete and biased. It preserves certain narratives while discarding others. Over geological time, the decay of memory compounds the decay of matter. Entire epochs of knowledge may vanish, leaving only subtle chemical or geological traces to hint at what once existed. What remains may be as ephemeral as the ripples in sediment, as cryptic as carbon spikes in geological layers, or as ambiguous as isotope anomalies in rock strata. These shadows of civilization are faint whispers of what was, and they require careful, imaginative interpretation to be understood. Chemical shadows and geological markers offer the most enduring evidence of vanished civilizations, yet they are almost always subtle and easily misinterpreted. Sudden spikes in carbon isotopes, anomalous distributions of rare elements, and unexplained changes in sediment composition may represent the only physical echoes of industrial or biological activity. These signals, however, are typically interpreted within natural frameworks, volcanic eruptions, asteroid impacts, climate shifts, or microbial activity. The possibility that they may represent traces of intelligence or technology is often dismissed as speculative, yet the sandcastle principle reminds us that the absence of clear structures does not imply the absence of past civilizations. Instead, it underscores the fragility of physical artifacts and the subtlety with which information can endure. Even if civilizations left behind monumental architecture or machines, millions of years of geological recycling would likely reduce these to scattered fragments, compressed strata, or chemical anomalies imperceptible to the casual observer. The sandcastle principle also emphasizes that impermanence is not synonymous with despair or futility. It is a warning, a lens through which to understand the relationship between humanity and time. By recognizing the transient nature of all constructions, we gain awareness of the true scale of our actions and the limitations of our influence. Civilization, in this context, is not measured by permanence alone, but by the ideas, knowledge, and questions it leaves behind. Even if structures vanish and memory fades, civilization can endure in subtler forms, encoded in DNA, layered in sediment, or preserved in the chemical composition of the environment. These enduring traces, however cryptic, serve as both warning and legacy, reminding future intelligences of the fragility of complex societies and the inevitability of change. Civilizations may also vanish because their very foundations are unstable. The sandcastle principle teaches that complexity is fragile, and that the systems supporting human societies, agriculture, industry, governance, energy networks, and information are vulnerable to cascading failures. Just as mountains erode and continents drift, social, economic, and ecological systems are subject to forces that can lead to collapse. The collapse may be sudden, triggered by climate, disease, or resource depletion, or it may be gradual, as inefficiencies, corruption, and environmental stress accumulate over centuries. Regardless of the mechanism, the result is the same. Knowledge is lost, records vanish, and the memory of the civilization fades. The Earth does not remember every empire, and even the most brilliant societies can be swallowed by time. Over millions of years, total erasure is the norm, not the exception. Geological processes, sedimentation, tectonic activity, erosion, and metamorphosis reshape the surface, burying cities, monuments, and artifacts beneath layers of rock and soil. Oceans, rivers, and glaciers act as both destroyers and preservers, dispersing material while creating new sedimentary records. Fossilization, typically associated with bones and hard parts, is rare for most human-made materials, especially metals and plastics that corrode or break down chemically. Even concrete, which seems impervious in human terms, is gradually leached by water and broken apart by freeze-thaw cycles and tectonic stress. Over tens of millions of years, the traces of an industrial civilization would be reduced to barely detectable chemical anomalies, subtle isotope variations, and slight disruptions in sedimentary layers. The echoes of a society that once burned brightly but ultimately succumbed to time. The sandcastle principle also applies to culture and memory. Languages die not only because speakers vanish, but because the contexts in which they are used change or disappear entirely. Records written on paper decay, ink fades, and digital storage becomes obsolete. Knowledge encoded in ephemeral media, dependent on fragile infrastructure or electricity, is particularly vulnerable. Oral traditions, while resilient, are also subject to distortion, loss, and selective preservation. Civilizations forget as much as they collapse, and memory is rarely linear or complete. What survives may be fragmentary, obscure, or misinterpreted, yet these fragments can provide insight into past societies if approached with imagination and rigorous scientific methodology. The lessons of the sandcastle principle extend to modern humanity. We live with the illusion of permanence, constructing cities, satellites, and digital archives that seem secure and enduring. Yet, even in our own era, we witness the impermanence of human achievement. Coastal erosion threatens massive urban centers, industrial accidents leave lasting but uneven environmental impacts, and digital infrastructure is vulnerable to obsolescence and decay. Viewed through the lens of deep time, the achievements of modern civilization may leave little more than faint chemical fingerprints, isotopic anomalies, and subtle disruptions in sedimentary and biological systems. The awareness of this fragility is not meant to evoke despair, but to instill a sense of responsibility, humility, and perspective. Beneath our feet lies a record far more vast, intricate, and enigmatic than the human mind can easily comprehend. The Earth itself functions as a colossal, encrypted archive, a palimpsest of events, processes, and potentially civilizations that have risen and fallen over hundreds of millions of years. Unlike a library, which is intentionally organized, catalogued, and preserved, the Earth's archive is chaotic, fragmented, and often inaccessible. Its pages are written not in ink, but in layers of rock, shifts in isotopes, subtle chemical anomalies, fossilized organic compounds, and the complex interplay of sedimentation and tectonics. Each layer is a record of events that unfolded over vast stretches of time, many of which may appear to us as natural phenomena, yet may conceal patterns that hint at intelligence, technology, or civilizations that have long vanished. We, as a species, have barely scratched the surface of this archive. The visible world, the cities, monuments, and landscapes we navigate daily, is only a thin veneer atop layers upon layers of geological memory. Even in areas that have been superficially studied, we have largely read only the most obvious pages, the top strata that are easily accessible and interpretable according to our preconceived notions of what constitutes evidence of civilization. We dig where we expect to find human artifacts, primarily near known archaeological sites, within regions where human activity is historically documented, or in locales where prior discoveries suggest the potential for more finds. This approach is natural and rational, yet it creates a profound bias. We see what we are looking for, and we overlook what does not fit our expectations. Much of the Earth remains unexplored, particularly in regions that are difficult to access, inhospitable, or submerged. Over 70% of the ocean floor, for example, has never been mapped in any meaningful detail. Vast swathes of continental interiors, remote deserts, deep canyons, polar ice sheets, and dense tropical jungles have never been examined with the tools necessary to uncover subtle signs of past life or intelligence. Even where we do conduct research, our focus is often guided by the assumption that past intelligence must resemble us, that is humanoid, metallic, stone-using, and city-building. As a result, potential evidence that exists outside these parameters, fossilized soft structures, chemical traces of industrial processes, unusual isotopic distributions, or organic constructs designed for longevity, may be misinterpreted, dismissed, or entirely overlooked. Consider the possibility that some traces of past intelligence may already exist in the data sets we have gathered, but have not yet been recognized for what they are. Geological surveys, core samples, and sediment analyses routinely reveal anomalies, metallic concentrations, unusual mineral formations, or isotopic ratios that deviate from expected natural baselines. Historically, the scientific approach has been to seek natural explanations first. Anomalous alloys may be attributed to volcanic processes, meteorite impacts, or chemical fractionation. Unusual isotopic ratios may be interpreted as indicators of shifts in climate, asteroid collisions, or organic decay. Yet, the sandcastle principle reminds us that evidence can endure even when all visible structures have vanished. Minute traces, chemical shadows, and altered sediment layers may be the only remaining signatures of a civilization that existed millions of years before humanity. One illustrative example comes from the mid-Paleocene, roughly 56 million years ago, during an interval known as the Paleocene to Eocene thermal maximum. Sediment layers from this time contain traces of platinum group elements, rare earth concentrations, and sudden spikes in temperature consistent with the rapid release of carbon. Standard scientific interpretations suggest volcanic activity or methane clathrate releases as possible causes. Yet, when examined through the lens of the hidden archive hypothesis, these anomalies take on a different significance. If an industrial civilization had existed at that time, operating at a planetary scale, its chemical byproducts could have left precisely these subtle yet measurable traces. The temperature spikes, isotopic anomalies, and unusual element distributions may be the faint footprints of technological activity, long since erased from view by sedimentation, erosion, and geological transformation. Entire cities, if they ever existed, could be reduced to barely detectable chemical and isotopic signatures. Concrete, metals, plastics, and other technological artifacts, subjected to millions of years of pressure, heat, and chemical interactions, would likely break down into their constituent elements. Streets, buildings, and infrastructure would be crushed, buried, or chemically altered to the point of unrecognizability. Yet even in such extreme degradation, traces could remain. Layers enriched in certain elements, localized isotopic anomalies, and subtle patterns in sedimentary composition could all serve as markers, if only they were properly recognized. The challenge is that these traces are not obvious, nor are they self-evident as evidence of intelligence. They require new ways of thinking, new methodologies, and a willingness to question assumptions about what constitutes a civilization. Scientific progress often hinges on anomalies, data points that defy expectation, observations that resist tidy classification. Anomalies challenge our frameworks, forcing us to reconsider prevailing paradigms and to explore alternative explanations. Yet, in many cases, anomalies are dismissed or ignored because they are inconvenient, inexplicable, or incompatible with prevailing theories. This reluctance to investigate anomalies may be one of the most significant barriers to uncovering the hidden archive beneath our feet. If we choose to revisit these outliers with open minds, integrating geological, chemical, biological, and statistical analyses, we may begin to uncover evidence that has been present all along, but misread or miscategorized. The Earth's archive is not fully silent, it is merely difficult to read, requiring both imagination and rigorous scientific inquiry to interpret. The bias of exploration also extends to assumptions about space and depth. Archaeological efforts typically focus on the superficial layers of sediment and rock, where human artifacts are most likely to be found. Yet the deeper we dig, the more we encounter compressed, transformed, and enigmatic layers that may contain the faint echoes of ancient events. Geological processes such as sediment compaction, metamorphosis, and tectonic shifting may obscure or distort evidence, rendering it nearly invisible to conventional methods. Similarly, deep-sea sediments conceal entire ecosystems, landscapes, and potentially anthropogenic or intelligent constructs, hidden under hundreds of meters of silt, sand, and rock. Oceanic exploration is particularly challenging. Water distorts perception, mud conceals structures, and crushing pressure complicates both observation and excavation. Even where rectilinear or geometric features are detected, Azores, India, Japan, or the Caribbean, the evidence is often dismissed as natural formations or anomalies rather than considered as potential remnants of intelligent activity. The hidden archive beneath our feet is not limited to chemical and mineral traces. Subtle biological markers may also persist. Fossilized shells, altered microfauna, and changes in isotopic ratios within organic layers may encode information about environmental modification, industrial-scale carbon emissions, or other forms of technological influence. Such traces are faint, requiring sophisticated instrumentation and analytical models to detect. Yet, over deep time, these biological and chemical footprints may endure far longer than any monument, machine, or city, precisely because they are integrated into the natural cycles of sedimentation and geological transformation. The Earth remembers, but it does so in its own language, a language of isotopes, chemical anomalies, sedimentary structures, and fossilized microorganisms. Learning to read that language is the key to accessing the hidden archive. One of the most fascinating implications of this concept is that our understanding of the past may be fundamentally incomplete, not because evidence never existed, but because it exists in forms we are not accustomed to recognizing. Misclassified alloys, unusual crystalline structures, and anomalous chemical layers may already reside in geological and oceanic databases, dismissed as natural oddities or experimental error. Entire civilizations could be represented in data that has already been collected, yet remains unanalyzed, misunderstood, or ignored. This possibility underscores the importance of interdisciplinary investigation, combining geology, chemistry, paleobiology, archaeology, and systems analysis to reinterpret the hidden record beneath our feet.
Exploration bias also affects where we choose to search. Human attention is typically drawn to regions of historical significance, areas of dense population, or sites known to contain fossils and artifacts. Remote regions, vast deserts, isolated mountain ranges, deep ocean basins, and the polar ice sheets remain largely untouched, despite potentially preserving evidence of civilizations that flourished in conditions radically different from our own. The Earth itself is not uniformly documented. Its memory is patchy, fragmented, and incomplete. Each new discovery has the potential to rewrite our understanding of what is possible, yet most of the planet remains unexamined, a vast archive lying in wait beneath sediment, rock, and water. If we embrace the idea of the Earth as an encrypted archive, then anomalies cease to be curiosities. They become potential messages from the deep past. Chemical signatures, platinum group element spikes, sudden shifts in isotopic ratios, and unexpected mineral concentrations may encode information about processes, intelligence, or events that are otherwise lost to history. Each anomaly represents a page in the planet's record, and each page is written in a language that requires both imagination and empirical rigor to decode. By revisiting anomalies, developing new detection techniques, and expanding exploration into previously neglected regions, we may begin to read the Earth's hidden story. The concept of the hidden archive also reframes our understanding of time. Geological time operates on scales far beyond human comprehension, and evidence of past civilizations must be interpreted within that context. A civilization that existed tens of millions of years ago would leave traces that are faint, dispersed, and transformed by natural processes. Its cities, monuments, and artifacts would be chemically altered, reduced to microtraces, or embedded in sedimentary layers inaccessible without drilling, coring, or advanced remote sensing techniques. Yet these faint traces may still carry information, subtle isotopic anomalies, altered mineral compositions, or patterns in sedimentation that hint at intentionality or technological activity. The archive beneath our feet challenges us to think not in terms of decades or centuries, but in terms of millions of years, where even the most ephemeral signals may persist long after the structures that created them have vanished. Throughout human history, myths have occupied a peculiar position in our understanding of the past. They are often dismissed as fanciful stories, cultural embellishments, or allegorical narratives, serving primarily as entertainment, moral instruction, or religious ritual. Yet, what if myths are far more than that? What if, rather than being merely stories, myths represent a sophisticated form of data compression, a way of encoding memory, knowledge, and warning across generations in a format designed to endure the erosion of time, language, and civilization itself? In this sense, myths could be the vessels through which the lessons and experiences of long-lost civilizations survive, long after their physical traces have vanished into the geological record. Consider the striking phenomenon of global flood myths. Across widely separated cultures, from the Mesopotamian epic of Gilgamesh to the Hindu tale of Manu, from the biblical account of Noah to Plato's Atlantis and the Hopi stories of world cycles, we encounter strikingly similar narratives.
civilizations overwhelmed by water, chosen survivors who escape destruction, sacred mountains where life persists, and the loss or concealment of profound knowledge. On the surface, these similarities may appear coincidental, the result of independent myth-making responding to local environmental events, such as river floods or tsunamis. Yet, the recurrence of shared symbols, the motif of floods, the presence of sacred or high places as refuges, the notion of select survivors, and the recurring theme of forbidden or lost knowledge suggests a deeper, perhaps global memory embedded within human storytelling. This consistency raises provocative questions. Could these myths represent a collective remembrance of cataclysmic events that affected human societies on a planetary scale? Geological records point to periods of abrupt climate change and environmental upheaval that would have been catastrophic for human populations. One example is the Younger Dryas, approximately 11,000 years ago, a period characterized by sudden cooling, massive glacial lake discharges, and rapid sea level rise. These environmental shifts would have inundated large swathes of habitable land, particularly along coastlines and river deltas, resulting in dramatic societal disruption, migrations, and population loss. Could flood myths, then, be a cultural echo of these real-world cataclysms, encoded in symbolic language that has survived long after the direct evidence of human impact has been obscured? If myths are data compression, their form makes perfect sense. Unlike records carved in stone or preserved on durable media, myths are designed to be flexible, memorable, and resilient. They survive not because they are precise in detail, but because they are structured to endure in oral and performative culture. Rhythm, repetition, and awe are essential components of this endurance. Repetitive narrative patterns, memorable characters, dramatic events, and emotional resonance all act as mnemonic devices, ensuring that the core signal of the myth, the warning, the memory, the lesson, is transmitted reliably across generations, even if the surrounding details are modified, misremembered, or mythologized. In this way, myths function as compressed memory. They reduce vast, complex experiences into symbolic, story-driven packets that humans can carry forward without the need for fragile technology or written records. The ancient site of Göbekli Tepe in modern-day Turkey offers a compelling parallel to this idea. Dated to roughly 12,000 years ago, it predates the advent of agriculture and challenges conventional timelines of human societal development. The megalithic pillars, carved with intricate depictions of animals, symbols, and abstract motifs, were deliberately buried by their builders, perhaps to preserve them or to conceal knowledge. This deliberate act of burial suggests that the site served a purpose beyond immediate utility. It may have been intended as a time capsule, a repository of symbolic knowledge meant to survive human forgetfulness or societal collapse. Göbekli Tepe exemplifies the principle that physical structures alone are not required to transmit knowledge, but can complement or reinforce the persistence of cultural memory embedded in myths. Forgetting myths, therefore, may be tantamount to forgetting warnings. Across cultures, myths often encode environmental, social, and technological lessons. Tales of floods, fire, cycles of destruction, and moral hubris may reflect repeated observations of natural catastrophes, technological failures, or societal collapses. By dismissing myths as fiction or reducing them to moral allegories, societies risk discarding embedded insights that were purposefully designed to endure when more conventional forms of knowledge are vulnerable. In this sense, myths function as a safeguard against total cultural amnesia. They survive the destruction of cities, the erasure of written records, and the reshaping of the landscape. The encoding within myths is sophisticated. Symbolism, allegory, and metaphor allow them to carry multiple layers of information simultaneously. Floods may signify actual inundation events, but they may also symbolize moral or technological overreach. Sacred mountains may represent both safe geographical refuges and metaphors for resilience or knowledge preservation. Chosen survivors may embody individuals or lineages capable of transmitting knowledge, culture, or genes to subsequent generations. Lost knowledge may encode warnings about practices that led to societal collapse, environmental mismanagement, or technological hubris. Viewed through this lens, myths are not static or arbitrary. They are dynamic, adaptive frameworks for remembering what otherwise would be irretrievably lost. The cross-cultural consistency of these narratives is particularly remarkable. The recurrence of flood myths, for example, cannot be fully explained by independent invention alone. While local environmental conditions may inspire similar stories, the strikingly parallel themes across Mesopotamia, the Indian subcontinent, the Americas, and the Pacific suggest either a shared ancestral memory or a universal human capacity to encode catastrophic experience in symbolic form. This universality hints at a principle that extends beyond cultural specificity. Myths are an adaptive form of information preservation, optimized for endurance in contexts where conventional records fail. The Younger Dryas provides an illustrative case. At the end of this period, roughly 11,000 years ago, abrupt climate change resulted in massive glacial meltwater floods, sea level rise, and regional extinctions. For human societies at the time, these events would have been catastrophic, reshaping coastlines, erasing settlements, and threatening survival. Oral traditions may have captured these cataclysms in the form of myth, encoding both the events themselves and the lessons learned, warnings about hubris, the fragility of civilization, and the need for vigilance in the face of environmental volatility. Over generations, the stories may have drifted into allegory, reshaped by cultural values, but the data embedded within them, the memory of rapid, destructive change, persisted. The persistence of myth contrasts sharply with the fragility of technological records. Stone monuments erode, paper disintegrates, and digital media can be lost to obsolescence, corruption, or the collapse of infrastructure. Oral traditions, by contrast, are remarkably resilient, capable of surviving millennia, even in the absence of formal recording. Their mnemonic features, rhythm, repetition, rhyme, and narrative structure allow them to endure through centuries of social upheaval. In essence, myths act as compressed archives, ensuring that essential knowledge is preserved even when civilizations themselves vanish. Göbekli Tepe and similar archaeological sites exemplify the complementary role of physical artifacts in reinforcing mythic memory. The deliberate burial of megaliths may have been an act to protect symbolic knowledge for future generations. These physical markers, embedded in the landscape, provide a durable reference point that interacts with oral tradition, reinforcing memory through ritual, storytelling, and symbolic association. The alignment of monuments with celestial events, animal symbolism, or environmental markers further suggests that these sites were designed to encode and transmit information over long timescales, much like myths themselves. The compression of memory into myth also offers an explanation for recurring motifs across otherwise unconnected cultures. Floods, sacred mountains, chosen survivors, and lost knowledge are patterns that appear repeatedly, regardless of geographic separation. Such universality points to underlying principles of human cognition, collective memory, and survival strategy. The human brain is attuned to recognize narrative structures, allegorical symbolism, and moral lessons, making myth an optimal vehicle for encoding complex, multi-layered knowledge that can survive repeated reinterpretation and transmission across generations. Forgetting myth, therefore, carries real consequences. In dismissing myths as mere fiction, we risk discarding encoded information that could inform environmental stewardship, disaster preparedness, societal resilience, and technological caution. The myths act as a bridge between the ephemeral nature of human civilization and the vast timescales of geological and environmental processes. They encode warnings about hubris, environmental mismanagement, and the impermanence of human constructs, lessons that remain relevant to any civilization navigating the fragile balance between technological advancement and planetary limits. Beyond floods, myths also encode cycles of rise and fall, warning against complacency and overconfidence. Tales of civilizations destroyed by their own excesses, gods punishing hubris, and recurring cycles of world-ending cataclysms may reflect real historical experiences repeated over millennia. The narrative patterns found in these myths, destruction, survival, and rebirth, mirror processes that can be observed in the geological and fossil record. Extinctions, climate change, and environmental shifts are not random. They follow discernible patterns that ancient storytellers encoded symbolically. In this sense, myths become an interface between human cognition and the deep time memory of the planet. Interpreting myths as compressed memory also changes our perspective on what constitutes evidence. While conventional archaeology prioritizes tangible artifacts, tools, structures, bones, and inscriptions, the mythic archive preserves intangible information, patterns, lessons, and signals of survival strategy. By analyzing common motifs, symbolic structures, and cross-cultural resonances, we may detect echoes of real events, technological insights, or environmental catastrophes. Myths, therefore, are not just stories. They are repositories of experience, encoding data in forms designed to survive when conventional records fail. In conclusion, myths are far more than entertaining tales. They are compressed memory, a sophisticated system for transmitting knowledge, warnings, and experiences across generations, even when physical structures and technological records are lost. Flood myths, recurring motifs of sacred mountains, chosen survivors, and lost knowledge suggest a collective human memory of catastrophic events, possibly reflecting real environmental upheavals, such as the Younger Dryas. Sites like Göbekli Tepe reinforce this concept, showing that symbolic and physical records can be deliberately preserved for future generations. Forgetting myths risks discarding vital lessons embedded in narrative, rhythm, and allegory. By understanding myths as compressed memory, we recognize that human storytelling is not merely cultural ornamentation, but a resilient, adaptive mechanism for encoding knowledge that can survive millennia, offering profound insights into the hidden archives of both human and possibly pre-human civilizations. In doing so, myths become both history and warning, entertainment and instruction, evidence and inheritance, bridging the deep past with the uncertain future in ways we are only beginning to comprehend. In contemplating the trajectory of life on Earth and the fragility of civilizations, one cannot ignore the profound lessons encoded in the planet's deep history. Among the most striking and unsettling of these lessons is the Permian-Triassic extinction event, the most severe mass extinction in Earth's history, which occurred approximately 252 million years ago. This extinction, often referred to as the Great Dying, wiped out more than 90% of marine species and roughly 70% of terrestrial species. Geological and chemical records indicate that this event coincided with a rapid spike in carbon levels, suggesting a sudden and extreme perturbation of the global carbon cycle. For decades, the prevailing explanation for this die-off has been massive volcanic activity in the Siberian traps, releasing enormous quantities of carbon dioxide, methane, and other greenhouse gases into the atmosphere. Yet closer examination of the sedimentary and isotopic records reveals anomalies that hint at a possible acceleration beyond what volcanic activity alone could account for. The cause, in other words, may not have been purely natural, or at least it may have been amplified by processes that remain poorly understood. This event stands as a stark reminder of the fragility of complex life and the vulnerability of even the most diverse ecosystems to sudden shifts in climate and chemistry. The fossil record shows that the effects were global and profound. Entire ecosystems collapsed, trophic chains were disrupted, and species that had thrived for millions of years disappeared entirely. This extinction serves as both a mirror and a warning, illustrating the potential consequences when natural or artificial processes push planetary systems beyond their thresholds of stability. Fast forward hundreds of millions of years, and we find ourselves in what geologists call the Anthropocene, a new epoch defined by the profound and unprecedented influence of humanity on the Earth's geology, atmosphere, and biosphere. In the Anthropocene, humans have become a force capable of reshaping the planet, not only in the short term, but with potential consequences that will be recorded in the geological strata for millions of years. Our fingerprints are visible in the form of plastics, microplastics embedded in sediments and soils, radionuclides from nuclear testing that have permanently altered the isotopic composition of the crust, and dramatic shifts in biogeochemical cycles, particularly nitrogen and phosphorus, due to intensive agriculture. The carbon spike we are producing today mirrors the patterns observed in past extinction events, raising the unnerving possibility that we are repeating arcs seen in Earth's deep past. Just as the Permian-Triassic extinction may have been accelerated beyond what was expected from natural processes, so too might our industrial civilization be driving rapid planetary changes that surpass the natural variability of the Holocene. Collapse, however, is rarely sudden in the way popular imagination might suggest. It does not arrive as a single catastrophic event, a thunderclap signaling the end of a civilization. Instead, collapse is a slow, insidious process, unfolding across multiple systems simultaneously. Ecosystems begin to unravel, insect populations decline, coral reefs bleach and die, forests shrink, and marine species vanish at unprecedented rates. Supply chains fracture under the strain of scarcity and environmental change. Climate destabilizes, producing feedback loops that amplify initial stresses, while human societies struggle to adapt to accelerating crises. Fires rage across landscapes rendered vulnerable by drought and mismanagement. Floods inundate areas where natural buffers have been removed. In this slow-motion unraveling, the decline of civilization is both predictable and terrifyingly familiar. The signs are all around us, if only we choose to see them. The graphs of biodiversity decline, carbon accumulation, deforestation, and rising sea levels trend inexorably upward. Yet, beyond these immediate concerns, there exists a far deeper and more profound question. What happens millions of years from now? If humanity vanishes, as all civilizations eventually do, what traces of our existence will remain? Will we be remembered at all, or will our impact fade into chemical shadows, sediment layers, and anomalous isotopic ratios indistinguishable from natural processes? The Silurian Hypothesis and related considerations suggest that it is entirely possible for an intelligent civilization to disappear almost entirely from the observable record, leaving only subtle signatures in the geological archive. Our plastics, radionuclides, altered soils, and atmospheric anomalies may endure far longer than any of our monumental architecture, but they will not narrate our story. To future intelligences, should they arise millions of years hence, these traces may appear as anomalies, curiosities, or even mythological elements interpreted through the lens of their own emerging understanding. Imagine a distant future tens of millions of years hence. The continents have drifted into entirely new configurations. Mountains that once towered above us have crumbled. Oceans have shifted, swallowed coastlines, and revealed new lands. Our cities have long since been reduced to rubble, consumed by vegetation, sediment, or tectonic forces. Satellites, once circling the Earth as symbols of our technological reach, have disintegrated or fallen into the oceans. All that remains of humanity may be microscopic shards of plastic, chemical anomalies embedded in sediment, and perhaps faint isotopic signatures that could only be recognized as artificial by an intelligence capable of detecting such subtle cues. These remnants would constitute our fossil record, a quiet and indirect testimony to our brief and intense existence. And yet, within this record, future intelligences may also perceive echoes of ourselves. Perhaps they will detect our chemical shadows and interpret them as evidence of intelligence. Perhaps they will reconstruct our history in mythic form as we reconstruct the past from sparse and enigmatic traces of civilizations long vanished. They may imagine gods or ancestors in the residues of our technology, projecting narrative onto anomalies just as we have done with Göbekli Tepe, flood myths, or the unexplained layers in the sedimentary record. In this way, intelligence is both ephemeral and recursive. It may arise, flourish, and fade, only to be recognized or interpreted by those who come after, long after its creators are gone. Civilization, then, is not a guaranteed endpoint, but a recurring spark. It is brief, intense, and fragile, a flare in the deep time darkness. Each civilization illuminates its environment, reshapes the biosphere, and leaves traces, but survival beyond a few millennia is never assured. The geological record demonstrates that life is resilient, but civilization is not. It is a pattern of rise and fall, a series of sparks that light the temporal corridor of Earth's history. The challenge for us, and for any intelligence that may follow, is to recognize the impermanence of these sparks and to understand that survival in memory requires more than dominance or technological prowess. It requires embedding wisdom into systems that can endure long after cities and empires have vanished. Thank you for joining us on this extraordinary journey through the universe on frontiers of infinity. If this glimpse into the unknown has sparked your curiosity, be sure to subscribe and join us, where we unravel the darkest mysteries of space.